Hi students, I am going to go over this problem again with you and also finish up the PowerPoint on acids and bases and go over the bicarbonate buffer system in the body. So looking at this question again, looking at letter A, we know that this is a buffer. And why do we know this is a buffer? Because we know that a buffer is equal to a weak acid plus the salt of its conjugate base, or a weak base plus its conjugate acid. Well, let's say it's the salt of a weak base. And the reason why we have this is because the weak acid is going to react with any base in our solution. Well, let's not use that kind of base. Any strong base that we add to our system, which is going to be our hydroxide, is going to give us water plus a little bit of weak base. And because of that, we don't have such a large, let's say, decrease in, I wonder how can I, y'all know I'm bad with the technology. I want to bring this page down, but I don't know how. All right, maybe if I just go down. Okay. No, I don't want to do that. I just want to go down. Let's get rid of this little box over here and let's finish writing. The conjugate base. Oh, I'm on the pen, right? Y'all know how I do with these pens and this. Okay, let's do this. Okay, it's not doing it. I apologize, students. Oh, that's right, I have to use this. So the weak, or let's say the conjugate base, which is going to be the A-, if it's reacted with a strong acid, which is essentially going to be a proton, then what we get from this situation is just a little bit of weak acid. And because we end up with water and some more weak base when we add a base, or just a little bit more weak acid when we add an acid, the pH remains constant. Well, remains, let's not say remains. Let's say the pH only changes slightly. Whereas if we were to simply add strong acid or a strong base, then the pH would change drastically if we were to add it to water. Now, let's take a look at letter A. And we see that A has, let's go back to our pen. A has HCN plus NaCN. So this is our weak acid, and here's our conjugate base, right? When we put this in water, what do we get in solution? Well, we get, because this is a weak acid, weak base, weak acid situation, we're gonna get a few things in solution. So in the forward direction, we end up with our proton, we end up with our weak base. Our conjugate base, plus our sodium. Is that it? Did we do them all? HCN. Okay, sodium. All right. Now, because this is a weak acid, we're just going to have just a little bit of the conjugate base, which is why we have to add conjugate base. So now that we have a lot of conjugate base and a lot of weak acid. So our species that we have in solution that are going to react is going to be the weak acid and the conjugate base. So A is a buffer. Now, let's take a look at B. B, we have HNO3. Let's go back. For B now, we have HNO3 plus KNO3. Now, when we're looking at these problems, we have two different solutions, right? And when you're thinking about these problems, remember I just went through the chemistry a little while ago, but you got to think about, how do we make that solution? How do we make that 1 molar solution? Well, to make that 1 molar solution, we had to take 1 mole of, let's say we scoop it up in our little scooper, 1 mole of this stuff. And to get 1 molar of potassium nitrate, we need to take 1 mole. That's my little spatula, scoopula, people. Don't make fun. And I put it in a beaker of water, 1 liter, right? And I dissolve. Okay? All right? So I'm going to put that scoop in my solution. And now I end up with a 1 molar solution. Now, if I take equal amounts of that, if I have 50 milliliters of each one, then I'll have equal amounts of both of these situations. Well, we'll have we'll have same amounts of our acid and base in solution. Now, when we look at what we have, we notice that we have a strong acid. HNO3 is strong. It's a strong acid plus the salt of its conjugate base. Now, you know that if I have a strong acid, then the conjugate base is going to be weak. And we know if we have a weak conjugate base, then it's not going to readily accept a proton. So what do we end up with in solution? Because we're in solution. What do we end up with in solution? Well, I end up with lots of protons, right? And lots of NO3. And a little bit of potassium, right? In solution. Now, notice what we have in solution. We have a weak base. A weak base. And we have an acid. This is strong acid with our proton. So this cannot be a buffer. We've got weak base, but we don't have its conjugate acid in this situation. So we do not have a buffer over here for B. Only because what we have in solution is not a buffer. Now, let's take a look at C. In C now, we see that we've got a weak acid. Excuse me. We've got a weak acid. Oh man, that looks horrible, people. Let me fix that. My hand is a little shaky, guys. I apologize. We have weak acid plus strong base. So we got weak acid, strong base. Now, in solution, what do we get? Well, we get a little bit of hydrogen ion. We get a little bit of CO2H minus. Oh, wait, I drew that wrong. I gotta put the H over here. H, because we lose the hydrogen that's connected to the oxygens. And we end up with hydroxide and potassium. And we end up with a lot of potassium and a lot of hydroxide. And a little bit of our acetic acid. So, yeah, we've got, what do we have in solution? Well, because, let's put this here. Well, I won't put that there. Let's get rid of that. Let's take a look at why I wanted to put that there. Well, for our weak acid, right? What do we end up with in solution? We end up with these two guys in solution, right? And I have now only a small amount, but I've got lots of base. So I've got some weak acid, but I've got a little bit, well, let's look at our concentrations over here. I've got half of the amount of strong base than I do weak acid. So let's get rid of this big arrow over here, because we didn't have as much strong base as weak acid. So what do we have in solution? We've got our weak acid and we've got some conjugate base. So even though we've got hydroxide in solution, oh, I forgot to put my plus on my potassium. Even though we've got hydroxide in solution, it does not contribute to our buffer, and it's only a small amount, and it's much smaller than the amount of weak acid, because we've got 1 molar. And if we know that we've got 1 molar of our weak acid, and it's a weak acid, we're going to have mostly weak acid in solution, and a little bit of the strong base that was, I'm sorry, not the strong base, the conjugate base that was created by the reaction with our strong base, because the hydroxide is going to react with the hydrogen, and that is going to be water. So we'll end up in solution, we've got CO2H, and we've got HCO2 minus. And we've got our potassium. And it does not react as a buffer. So, it doesn't react as a buffer. And as a part of our buffer, it's just a spectator ion. So, yes, C is a buffer. Now, let's take a look at D. Let's take a look at D. Now, D, what do we have? D, we have, I think I was calling that the wrong name. That wasn't acetic acid. That was methanoic acid. For C, that's methanoic acid. For D, we're looking at acetic acid here. So, what do we have? We've got our acetate, which is our conjugate base, or the base of acetic acid. So we've got CH3OO2Na. So this is going to be, let's say this is a weak base, or it's not a weak base, it's the, oh gosh, we've got, let's call this the conjugate base of acetic acid. And we have HCl. Well, when we react these two together, what do we get in solution? Well, in solution, all of this is going to dissolve completely. Why? Because it is a salt. Remember, it's the salt of conjugate base, and so it's going to completely dissolve to give us acetate plus sodium. And this is a strong acid, so it's also going to completely dissociate. And so because we have acetic acid is what? Is it a strong acid or a weak acid? It's a weak acid, so its conjugate base is going to be a strong base. So because it's a strong base, it is going to steal that hydrogen in solution and will actually end up with some of this in solution as well as in salt, right? So because we have a lower amount of HCl, we're not going to use up all of our conjugate base. We're still going to have half of it remaining. So we're going to have equal amounts of conjugate base and weak acid, right, in solution. So, yep, this one is also a buffer, okay? Hopefully that helped to clarify that slide just a little bit more in case you didn't catch it in class on last Thursday. Okay. I do believe we went over this slide as well. We want to find, whenever we use, whenever we're finding or looking to make a buffer, we want to pick the pKa that's closest to the buffer, the pH of the solution that we would like to buffer. Propionic acid, if we didn't have any acetic acid in the lab, then we could use propionic acid. Although it would not be as useful a buffer because its buffering range would be a little bit lower. So what happens in our blood? We have, in our blood, we have to maintain a certain pH. And that pH is 7.35 to 7.45. And if we have too much acid or too much base, we could have, it can result in death. So where do we get carbon dioxide from in our bodies? Well, we continually produce carbon dioxide as a product of cellular metabolism. So what do I mean by that? Whenever we carry out respiration and you break down glucose, you end up with carbon dioxide and water. So what does our body do with it? Some of that is carried to the lungs for elimination as CO2 gas, and some of it actually dissolves in the body fluids such as plasma, saliva. And when we dissolve CO2 in water, if you guys remember, we form carbonic acid. So we see here with the number 1 that we've got our first reaction in which CO2 dissolves in water to give us carbonic acid. Notice that it is a reversible reaction. Once we have carbonic acid in solution, it can easily dissociate to give us the bicarbonate and the hydronium ion. So that is our second reaction. So there are 2 steps in this process in which we have CO2 that dissolves in water to give us carbonic acid, which then dissociates or ionizes to give us bicarbonate and hydronium ion. Our kidneys also supply a portion of bicarbonate ion as it's forming urine. So we have CO2 that's produced in our cells, and our kidneys produce bicarbonate when necessary. So we have this buffer system where we've got CO2 made in our body cells and bicarbonate made in our kidneys, and we have this buffer system in all of our body fluids, and except for the ones that require a different pH, such as in our stomachs and in our pancreas creates bile, and then it's found in our small intestine. So if we have any excess acid or hydronium entering the body, then the bodily fluids is going to react with it's going to react with the bicarbonate. Remember, the buffer, if we add acid, then the base in the buffer is going to react with the acid, and we will have a shift in our equilibrium to the left. Okay, and if we have a decrease in our hydronium concentration, then our pH is only going to change slightly if we don't put too much acid in the system. Now, if we have excess hydroxide or base that is entering the body, it is going to react with the carbonic acid in the buffer system. And once it reacts with the acid, then the reaction shifts forward, unless we have a large amount of base added, and then our pH is going to change. So we resist changes in pH by shifting this buffer system when in the presence of an acid, strong acids, or strong bases. So how the carbonic acid concentration is related also to the partial pressure of carbon dioxide. So when there's too much carbon dioxide present in the blood, rising CO2 levels, it's going to increase the amount of carbonic acid and shift the reaction forward to produce more hydronium. Well, if we produce more hydronium, then we end up having a shift in the pH, and the pH is going to decrease. If we have too much CO2 in our body, we end up with a problem called acidosis. If now the CO2 levels in our bodies go down too low, as in the situation with hyperventilation, when you're and you're letting off too much CO2, then that shifts the equilibrium to reduce the amount of acid, and we end up increasing the blood pH, and this is a process called alkalosis. So here are some ways to so we have different types of acidosis. We either have respiratory acidosis, where we end up taking in too much carbon dioxide, or metabolic acidosis, where we take in too much acid. Notice the treatment is just by adding some sodium bicarbonate. Some people who have kidney problems have to take sodium bicarbonate pills because they tend to have high acid in their urine. Respiratory alkalosis, now meaning that the pH is high, can come from having too little CO2 in the blood, and the metabolic alkalosis occurs when we have too little acid in our blood. Okay, so take a look at the slide and become familiar with it, especially if you're going to be in the health profession. This is something that would be useful for you to remember. So, during stress or trauma, a person can start to hyperventilate. The person might breathe into a paper bag to avoid fainting. Complete the sentence to describe the changes that occur in the blood pH during hyperventilation. So the word is during. My pen is not working. The word is during hyperventilation, right? So if it's during hyperventilation, then that means you're and what happens to the CO2 levels in the blood? Right. It will increase. Well, if the CO2 levels in the blood increase, then the carbonic acid levels are also going to, I said increase, right? I'm sorry. Hyperventilation, we end up losing too much CO2. So the CO2 level in the blood decreases, making the carbonic acid level decrease. And if we make the carbonic acid level decrease, the hydronium ion concentration decreases. And if the hydronium ion concentration decreases, then the blood pH goes up or down. Right. The blood pH is going to go up. So what do we have for our answer? All right. So that's during hyperventilation. What happens, do you think, while the person is breathing into the paper bag? Well, breathing into the paper bag causes you to take in carbon dioxide that you're breathing out. So if you're taking in more carbon dioxide, then the carbon dioxide level increases, the carbonic acid levels increase, the hydronium ion levels decrease, and then the pH now decreases. Okay? So the equilibrium in this reaction, when we actually hyperventilate, is going to shift in what direction? It's going to shift to the left. While breathing in the paper bag, the equilibrium is going to shift in what direction? To the right. All right, folks, that was it. I wanted to make sure I finished up with that. I didn't want to leave you hanging before your next exam. Please check Blackboard for the exam review, and I will not be at the exam on Monday. There will be a proctor coming to take the exam. Be sure to have a pencil and a calculator, and you'll be provided with everything else. And I will see you all. I will see you all on the final exam. If you need to come see me, email me.